So let's see how far we can get to updating the beta prior today, but we definitely should start. We have about 13 minutes left. So earlier I was talking about how to use what is a beta distribution and how to specify a beta distribution to represent your prior belief if you're going to use that as your prior distribution. So that's step one. Remember, we have 3 steps for Bayesian inference. So now go to step 2. So step 2, again, is still a binomial experiment, right? No matter whether you're going to change your prior distribution from a discrete one to a continuous one, the data is the same. And we're using the same data model for it, which is a binomial experiment. So again, the likelihood, it's really important to use it because it's a function of the unknown parameter. It will help you to derive your posterior in a minute. You will see it. Okay, right? So recall that for a discrete parameter, we have equation 15. That was what we used earlier if you have a discrete prior, remember? And we use summation here because you have a discrete partition of the set parameter space. Remember, we have 6 different values, so we're doing that over here. So for a continuous P, obviously we cannot do summation, but you're gonna replace the summation sign with the integral, okay? And that integral is integrating over P, right? Because P is the unknown parameter. So the range is from 0 to 1. Okay. And for now, we're gonna work with the simpler case. I would say simplified version here that we're gonna first of all assume that the denominator is fixed. We're gonna talk about this in like maybe next time. And I want to introduce you the pretty commonly used proportional expression of the posterior. So if you look at this carefully, the left-hand side is the posterior distribution, right? P given Y. And it's proportional to the prior multiplies with the likelihood. Okay? The proportional comes in place of the equation is because we sort of didn't compute and we sort of saying that this is fixed, so it's a constant, so that makes the equation equality, I should say, equality sign to the proportional sign. Okay? I will talk about why we can use the proportional sign next time, but for now, this is what we're going to focus, and I will show you some of the derivation first, and then we're going to do the reasoning of why you can use proportional later. So what you need to know here is that you will see later that the denominator is actually a fixed constant, and take that. If that's a constant, it can go into the proportional sign, right? We just don't know what it is, but it's not something about P anymore because we integrate out P. Okay? So again, so that's why I was saying earlier, it's super important to think about everything in a function in terms of P. Okay? Because anything is like not in, like everything that is not dependent of P can be a constant. And that helps a lot in our derivation. So the prior is a function of P, right? So that should stay. We cannot ignore that. The likelihood is a function of P, right? We just talked about it, how you should express that. The key here is the denominator, which once we use the integral sign over here, as you can see, this, because we're doing integration, P goes away. So whatever comes out, it can be considered as a constant for P because it's independent of P. Okay, so we're going to derive next time. It is indeed a constant. Okay? But the big picture here is that because we integrate out P, it's independent of P. So it can be considered as a constant for P, and that's why we can use a proportional sign. Okay. So this actually, if you're a little bit confused, think again about the review that we did the other day. That if you have the joint distribution of two unknown variables, right? If you have joint of, what was it again? Let's see. If you have the joint, you have the joint, right? And in order to get the marginal, what do? You integrate out the other one, right? So if I want to have, if it's continuous, okay? That's what we do, right? Yeah. So what we saw earlier, so let me try to rewrite what I did over there. I think it was, let's see, do it one by one. What we did is, right? That's what we did, okay? And if you don't really see how this plays out in what I was talking about, getting the marginal should be integrating out the other one in the joint. Recall that, so this stays, but remember, this is, we write it in terms of likelihood because we want to express it in terms of P, right? But what it was before, it was, right? Yeah. So the likelihood is the data model, and the data model is this, right? This is what the data tells us. So if I explain this way, I think now it's easier to see that this will become, let me just use a different notation. This will become the joint of Y and P, right? And now I integrate out P, what do I have? I have the marginal of Y, right? And it's independent of P, so I can consider it as a constant. So this is true for any kind of model, actually. So here I'm using P, but if you think about P as theta, which is the generic parameter that we use, this is true for any model. But next time we're going to derive it for the binomial case. I can let you know to see in detail of why it is indeed a constant. Okay. Make sense? Okay. So I hope now you can buy the idea that we're okay, that as long as we consider this as fixed, we can convince us this is fixed because we integrate out P, then this whole thing, which is in the integration sign for the continuous case, can go into the proportional sign because it's a constant. It's a constant in terms of P. Okay? So that's why it's super important, I think, to think about the prior, the likelihood, and the posterior as functions of the unknown parameter. Okay? Because that can help you to convince a lot of things. And I think that can also help you to stay on track with a lot of different information, new and old, together. Okay? Great. So once we can do this, we are able to start to derive the posterior. Okay? So this is the posterior. It's a proportional sign, but because what is left is a normalizing constant, we don't have to worry about it for now. So remember, the prior that we pick, not together, I picked for us, is this particular beta distribution. So A is 306 and B is 256. And the likelihood function is a binomial. Okay? So now we can start deriving. And when I'm saying deriving, especially we know from equation 17, that's what the posterior should be. It's pretty straightforward that as long as I put in whatever the PDF for the prior, right? And whatever the likelihood function from the binomial, I can start to derive to see what will be the distribution for the posterior, right? So let's see. I give this to you, pi P is, so that's the PDF of the beta distribution. The likelihood is this. And I will just, since we only have like 4 minutes left, I actually will ask you to do the exercise now in class. Try to do it based on the information that I've provided here. We're trying to derive the posterior. We have pi P to be a beta. The LP, which is the likelihood, is from the binomial function. I ask you now to try out how to derive it. we might not be able to get to the answer today, but it will be a good place to end, I think. So we should try this. And when we come back next week, we're going to continue with the derivation, and then, of course, go to what I said, the details, say, like, why that is a constant, how I can treat that constant as what, and how to do inference. Okay? But this is more like algebra, I think, algebra exercise. Yeah. So just try it and come to a form that you think you can start guess what the posterior distribution is. And we can end here soon. I should also say, since now we're using the proportional sign, and I've been trying to emphasize the point that whatever can be considered as constant in terms of p can go into the proportional sign. Right? So a quick hint, this is constant, right? It's a choose function. You have to do the factorial, it's complicated, but it is a constant for p. Right? This also is a constant. It's the gamma function that I talked about before. Right? So those, for now, don't worry about it. They will go into the proportional sign. So what's left for us is this two terms and this two terms. And as we were talking about the PDF of beta before, the really main reason of why we want to use beta distribution for the binomial likelihood is because the kernel, which is the part that is about the unknown parameter, they have really similar structure. Okay? And it is indeed this structure that we're going to see next time that we're going to arrive at a posterior distribution to be a beta distribution. It's another beta. It's going to be different from before, but it's a beta distribution. And that is what makes the beta distribution a conjugate prior for binomial likelihood. Because you start with the beta prior, you end at another beta distribution, which is the beta posterior. Okay. All right, so I think I'm going to end here today. And also, just a quick announcement, I posted homework 1 and on Moodle, and I made it due 1 week from today. Things should be okay because most of the material, every material is from the introduction, so we wouldn't be too difficult to do. But I have office hours next week if you have questions. I also assigned 2 our courses on data here, and yeah, so take your time to do it. I think it will be really good practice for people, especially the people who haven't done much of our programs. Okay, and yeah, just do it and you're gonna get the credit. I can see you complete it. Okay, all right.